Okay, so let's continue again for this graph connection Laplacian and the vector diffusion maps. And the focus today will be establishing the theoretical foundation of vector diffusion maps and graph connection Laplacians under the manifold setup. So those are the relevant papers that you have interest. You can take a look, and I will do some summary of things. And the background knowledge that you need to understand how to analyze the algorithms using differential geometry can be found here. And those are the textbooks that I highly recommend if you have interest. So let's start with the mathematical model about the vector diffusion map algorithm that we discussed in the previous two lectures. Okay, so the manifold model we consider will be a d-dimensional manifold isometrically embedded in RP. And we assume that the manifold is smooth and compact. And the metric is induced from the canonical metric in the ambient space. And to simplify the discussion, we will assume boundary free. But all the analysis, all the results can be generalized to the boundary case, but we will ignore it. So we use the notation Tm to be the tangent bundle, Om to be the frame bundle, and the Pyx to be the parallel transport of the tangent bundle from X to Y. Okay, so a very quick recall about what tangent bundle or frame bundle are. So tangent bundle, intuitively you can think that for a manifold as a geometrical object, at each point you attach it a vector space that describes how you change from one point to another. Okay, so this is a tangent space, a vector space, and at each point you attach one. So pictorially, sometimes we draw things in this way. M is a manifold, and this is a tangent bundle. At each point, you just attach a vector space. Okay, and a section is a vector field. But in practice, well, how to represent a vector in a tangent space? Usually it's just a vector space, but you don't know how to represent it. So we consider a notion called frame bundle, that is, you attach at each point all possible orthogonal bases of the tangent space. Okay, all possible orthogonal bases. So you know, for each d-dimensional vector space, all the orthogonal bases will form OD, the D's dimension of the orthogonal group. And if I give you one point, which gives you one basis, which is represented here, one basis, then what you can do is use this basis to represent this vector by its coordinate. So this is what you learn from linear algebra. And if you change one basis from one to another, you get another basis. Then obviously you get another coordinate. So you have different coordinates describing the same point using different bases. That is the key ingredient you learned from linear algebra. Okay, so the key question that we need to ask before we study vector diffusion map is how to differentiate a vector field. So how do we do so in multivariable calculus? It's kind of simple, right? So if you take a vector value function, x, the derivative of x at small x, one point, in the direction v is what? You simply move the point x by a bit in direction v, and you do the difference subtraction, and you divide it by t. That is how you do the differentiation. Easy. But can you just do a generalization of this formula to the manifold setup? Unfortunately, the answer is no, because the manifold is nonlinear. So x plus tv does not make any sense. However, we can, and how to make this a sense in general in the manifold setup? What we can consider is, first, gamma is a linear curve in the Euclidean space, x plus tv. And this trajectory can somehow be applied or be generalized to the manifold setup. Because this gamma at 0 is x, and the gamma prime will be v. So if you think in this way, and notice that when we talk about the direction v in Rn in the Euclidean setup, it is actually meaning that this v is on the tangent space, because the tangent space of Rn is just Rn. Therefore, you can just consider a generalization of x plus tv to be a curve in the manifold such that gamma 0 is x and its derivative at 0 is v. Then this is how it looks like pictorially. You have a point at gamma 0 is x, and you have a trajectory, and the derivative at 0 is v. And then somehow we can replace x of x plus tv to be gamma of t. However, this is still insufficient for us to generalize the differentiation. Why? Because the vector field, the vector space at x and the vector space at gamma of t, they are not comparable in general. They are not comparable. So in general, you cannot say, okay, how to do the subtraction. This doesn't make any sense. So to do the generalization, or to understand, or to consider differentiation of a manifold, of the vector field on the manifold, we need to do something more. And what is that something more? We need to know how to compare different tangent spaces. So in general, the tangent space are not directly comparable. That is, we cannot compare or subtract u by v directly. So in this case, although pictorially or visually they look similar, but you cannot really do subtraction. So overall idea is trying to find a way to move vectors along curves on a manifold in a consistent way so that we can compare vectors in different tangent spaces, and so that we can achieve the notion of how the vector field changes from one point to another. Okay, so we will consider Levi-Civita connection, and which is a very specific connection under the differential geometry framework. And the connection itself is a big field, and we will not go into it because that is too much. But you can find a lot of literature nowadays to describe what it is. And it is a very, very basic fundamental notion in differential geometry, Riemannian geometry, that helps us to do different kinds of analysis. So intuitively, a connection is just an operator that assigns two vector fields to a new vector field. That is it. It's called connection. Okay, and you can understand it as a derivative of y in the direction x. But what does it mean? It's very abstract. We need to make it concrete. So mathematically, it is how it is defined. It is an affine connection is a bilinear map, so that you have xy maps to nabla xy. But we cannot just do it because there are so many different kinds of bilinear maps. We need to assign some more conditions. The condition is we need to respect derivative differentiation, in particular Laplace rule. So we say, suppose I give you a function f, which is c infinity, then nabla f xy is f nabla xy. That is, in the differentiation, it is linear. But in y code, in the y component, the Leibniz rule is satisfied. So that is what a connection, a affine connection is. And suppose we impose some more conditions that respects the metric. Then, and it is torsion free. So that is called torsion free. Suppose these two conditions are satisfied. Then this connection is called Levi-Civita. And why is Levi-Civita connection good for us? First, it is unique for Riemannian manifold. And we are working with a Riemannian manifold. And this uniqueness, well, will allow us to say, okay, that is the one we are working with. And the metric condition guarantees the inner product is preserved under parallel transport that we will discuss in a bit. And the torsion-free condition will guarantee some kind of symmetry in curvatures. And that's kind of Yankee identities, the first one, second one, and so on. They're all very useful in different applications. And it helps us to get a simpler calculation. For example, the Christopher symbols are fully determined by the metric. Okay, and you can easily define a geodesic, which satisfies this condition, and you can define coordinate, so that you can describe how the manifold locally is charted or parameterized, and so on. There are many good properties, and you can find a lot of useful information in the text. Okay, so if you combine with coordinate calculation, then technically you can analyze the algorithm, and that is what we are doing. We will apply all this to analyze the vector diffusion map algorithm, graph connection Laplacian algorithm, and so on. Okay, and then we introduced a notion called parallel transport. What is parallel transport? So given the Levi-Civita connection, we can get a parallel transport which intuitively describes how to move a vector along a curve so that it remains parallel according to the connection. This is intuition. There's no mathematics, right? It's just kind of what are you talking about? Okay, parallel, and well, looks like parallel is the desired notion for comparison. Very good. But how to make it happen? So mathematically, that is how we do it. Suppose I give you a smooth curve gamma and a tangent vector v at gamma 0. What is a parallel transport? Parallel transport is finding a vector field v along the curve satisfying this equation. And this equation, if you write everything down in coordinate, you will see it is a nonlinear ODE. This is the initial value. This is the differential equation. And what you do is just solve the ODE, then you can find the vector field. So that you start with a vector v at gamma 0, and you move it along the curve. And you know that because it's nonlinear, it may not always exist. It may not exist forever, right? So you may find some time and so on. So some topological conditions, blah blah blah, will come into play. And those will be something you learn from differential geometry, and we will not dig into it. The key information we want to say is this condition actually says there is no change in the direction dictated by the connection. There's no change. When you move v from one point to another according to on that curve, actually it does not change. It does not change. This is what we call by parallel. Okay. Although if you look at this picture, this is a circle S2, and if you just visualize it, you see the direction seems to change, right? And but the good point is it assigns to each differentiable path gamma a linear isomorphism in between the initial tangent space and the tangent space at gamma of t. And this isomorphism tells you how you map one vector in one point to another in a canonical way. And since it's Levi-Civita, the isomorphism will preserve the inner product, like I mentioned before. And in this way, you know how to map one point to another. One vector at one point to another point. And this movement will respect the connection or respect intrinsic geometry. So, finally, after maybe 5 minutes, I hope so, only 5 minutes, we can differentiate a vector field, or called covariant derivative. What you do is you take a vector field at x in a direction v is defined in this way. That is, at gamma of t at time t, you just use parallel transport to move it back to x and divide by t. And that is the covariant derivative. So finally, we get a notion called derivative. And there are many further details. Maybe we will use them in the future lectures and we'll discuss them in the future. But now, just an FYI, for example, parallel transport depends on the path and the underlying connection in closed curvature. For example, you start at this point on the equator, and you have the vector pointing to the north, and you move it in parallel transport, move to the north, and then you move it down along another path, coming back to the equator, and if you move it back to the original point, you see you generate an angle. But if you move A to the North Pole and you come back following the same trajectory, then you get the same vector. So the trajectory gives you a lot of information, and some ideas like holonomy and so on will be related. But we will discuss them in the future when we need them. And all the above discussion, we only focus on tangent bundle, frame bundle, but they can be generalized to more general vector bundles, principal bundles, fiber bundles, and so on. But we will discuss them when we need them.